Hi, everyone. Welcome to our talk on empowering Zillow's developers with SelfService ETL. My name is Derek Gorthy. I'm a senior software development engineer on the Zillow Offers data engineering team. I've been working at Zillow for about 2 years now. My background is in developing highly scalable data pipelines and machine learning applications. I have over 4 years of experience using Apache Spark, and this is actually my second time speaking at this conference.
I'm Yuan Feng. I'm a software development engineer at Zillow Group. I'm working on building tools and datasets to empower users with big data.
So let's take a look at what we're going to cover in this talk. First, I'll discuss how we think about self-service ETL. Next, I'll cover the core components of our self-service architecture. Then, Jan and I will each go over one self-service implementation here at Zillow. Jan will cover Zetless, a self-service tool built for data analysts, and I'll cover Zagger, a solution catering to our data producer and data engineering teams. Finally, Jan will wrap up the presentation with next steps and key takeaways. Here at Zillow, we're reimagining real estate to make it easier to unlock life's next chapter. I'm sure many of you are familiar with Zillow from Zillow.com or the Zillow app, but we also offer customers an on-demand experience for selling, buying, renting, and financing with transparency and a nearly seamless end-to-end service. Zillow is the most visited real estate website in the United States, and we're looking to hire 2,000 people this year. So if you're interested in learning about career opportunities, feel free to reach out to either Jan or myself or visit our career booth at this conference. So this diagram represents the broader context in which self-service ETL exists within Zillow. I'll come back to it into a bit more detail later on, but I want to focus on this bottom right section for a minute. Last year at this conference, one of my colleagues and I presented on how Zillow Data Engineering designed the next generation of our data pipelines. One core component of this design was a library of modular Spark processing blocks that could be chained together in any order. This library gave data engineers an abstraction on top of Spark and a toolbox of common transformations. Throughout this talk, you'll see how we've expanded on this idea of abstraction and modularity, this time at the orchestration layer, in order to make it even easier to build high-quality data pipelines using the tooling that we've developed. So what is self-service ETL? Low-code or no-code ETL solutions have been around for years. So when we talk about self-service ETL, we mean a tool that can transform a definition of a data pipeline from some sort of user interface and output actual executable code. The goal here is to abstract away the complexity of orchestration, data processing, CI/CD, and other tasks that go into getting from that user interface to a deployed pipeline. As we thought about what a self-service ETL solution should do, we broke down the process of transforming a configuration into a functioning pipeline into 5 steps. I'll briefly go over each of these steps here, and then we'll take a deeper dive into each later in the next slides. So the first is the user interaction layer. This is where the user implements the pipeline configuration. It can be anything from a fully fledged UI to a JSON blob that's checked into a Git repo. The second is the interpretation layer. This is the process of taking a config, parsing it, and inferring any details of the pipeline definition that were not explicitly stated. The third is a pipeline metadata store. This is a persistence layer that stores the parsed pipeline definitions. The fourth is a rendering layer. This is the process that takes the metadata representation of a pipeline and constructs an executable file or files from the pipeline definition. The fifth layer is the orchestration and execution layer. This is the deployed pipeline that runs on a schedule in the batch case or is processing streaming data in the streaming case. You'll see that we bucketed these steps into 2 categories, opinionated and unopinionated. So by opinionated, we mean that this is the part of the process that is dependent on the structure in which the pipeline is defined. It is subjective and is built to accommodate its intended audience. By unopinionated, we mean that anything beyond this point is objective and it has no awareness of the input structure of the opinionated component. In short, this allows data engineers to bring their domain knowledge of orchestrators, Spark jobs, or CI/CD to create modular reusable components that are used by the opinionated systems. So now that we've looked at this holistically, let's dive into each component. The user interaction layer is where we tailor the experience to the users of the UI. Jan will demo what one of these UIs looks like later on in the presentation, so you'll get a much better idea of how we're understanding the needs of a user group and then tailoring this front end to those needs. We wanted to move away from the one-size-fits-all model that seems to be common in open source self-service ETL solutions that we evaluated. For example, data analysts prefer a UI experience that shows what processing blocks are available to them and provides some of the most common configurations to these blocks in a simple, easy-to-use interface. As a data engineer using this service, I really don't need a fully fledged UI to create my pipeline. I can interact with tools like Terraform that allow me to create multiple pipelines quickly and more quickly than you'd be able to through a UI. And I'll also want to be able to provide my own custom code or configurations when needed. The next point that we want to underscore here is that the UI must improve the developer experience of its users and that different groups of users need different things from a user interface. Moving on to the interpretation layer, this is where the configuration from the UI is parsed into a standard pipeline definition that can be consumed by the downstream process. One important point here is that given the modular design of this system, we can actually implement any number of parsers. So the only requirement of a parser is that it generates a standard pipeline definition, and how it gets to that is entirely up to the interpreter. To see how an interpreter can be useful, here are a few examples. So let's say that I want to provide users a few options for when their batch pipelines can run. Let's say hourly, daily, and weekly. I can provide these three options in a dropdown, and the interpreter will take care of the conversion from each option to a cron expression that is required by the orchestrator. For a second example, let's say that a data producer team has asked me to create a processing block that will transform their JSON data into Parquet format. As a stopgap, I can quickly create a script that does this conversion, add it to the interpreter, and make it available to the team. Over the course of the next couple of weeks, I then develop a well-tested Pipler data format conversion block, and I want to replace the original script that had been used as a stopgap. All I need to do is update the interpreter to reference my block, and the next time the pipeline config is synced, the pipeline will automatically be updated to reference my well-tested block instead of the stopgap script, without the data producer team needing to make any changes on their end. So these are just a few examples, but we found that embedding assumptions into the interpreter allows for a much simpler pipeline configuration experience. Moving on to the pipeline metadata layer, this is a persistent store of unopinionated standard pipeline definitions. This intermediate step serves a couple of purposes. So first, if a user is looking to create an Airflow pipeline, they only need to create the parser that generates the standard pipeline definition. And I'll cover why that is in the next slide. Second, this allows us to start building tooling on top of the metadata store. If we want to go back and look at all of our data pipelines spread across multiple orchestration engines today, we now no longer need to go back into each individual engine's metastore. Instead, every pipeline definition is stored in a central location, and this allows us to better understand things like data lineage, the dependencies between pipelines, and how we can more efficiently schedule pipelines when we understand their upstream dependencies. Third, this allows us to serve up current pipeline definitions across multiple user interfaces. If a team has created a pipeline through one user interface, like Terraform, it could later be viewed through the Zetless UI, giving users a seamless experience across our platform. Moving on to the rendering layer, this is the stage that's responsible for transforming the abstract standard pipeline definition into executable code. As we build out support for more orchestrators, we now only have to implement an orchestrator's renderer once. Let's dig into why this is a simple but powerful concept. So first, this allows for the flexibility to move between orchestrators. Traditionally, if you wanted to move from one orchestrator to another, you'd need to recreate that pipeline file in the new orchestrator's format. You'd basically need to entirely rewrite that pipeline for the new orchestrator. This process is tedious, and there's a lot of work that goes into checking that the new pipeline is equivalent to the old one. However, if you go through our pipeline renderer, you have the ability to produce that pipeline in any supported orchestrator without needing to understand that orchestrator's syntax. Now, second, this solves for the problem of major version upgrades in an orchestrator, where things like package structure, class names, and function inputs are likely to change. Instead, you can build out a renderer for the new major version and in bulk, upgrade your pipelines to that new version. Now, finally, we have the orchestration and execution layer. This is where the pipeline is deployed and how processing steps are run. In our presentation last year, we talked about how one of the key components of our next generation data pipelines is the development of our pipeline processing library. In order to standardize and improve the quality of our pipelines, we're continuing to develop a shared Apache Spark processing library that provides plug-and-play processing blocks. These processing blocks can be arranged in any order and provide data engineering and other teams the ability to run high-quality Spark code with no development cost. Like I said earlier at the top of this presentation, this self-service ETL solution is an extension of that same concept, where we're looking to provide an abstraction on top of the orchestration layer so that it's even easier to create high-quality data pipelines. And with that, I'll hand it off to Jan to discuss Zetless.
Thank you, Derek. Zetless is short for Zillow ETL as a service. The motivation of building Zetless is to provide data scientists, analysts, and anyone who doesn't necessarily want to code with a reliable UI-based self-service tool to automate the SQL-based workflows. Zetless has multiple features. Firstly, since it is UI-driven, users can quickly prototype and deploy their jobs. Also, Zetless supports job monitoring and alerting functionality, which can send alerts through email opportunity when a job fails, or a job fails to finish within a certain amount of time. Besides that, Zetless has a job validation service which can catch most of the errors before a job can be successfully submitted. In addition, Zetless is integrated with multiple internal services like Data Portal, Zodiac Team Ownership, Luminar Data Contract Platform, and so on. Finally, Zetless is scalable and expandable. We are continuously adding new task types to Zetless to expand its functionality. In the next slides, let's watch a video to see how Zetless UI works by creating a new job. Now we'll go through a job creation process to demonstrate how Zetless works. We need to click this new job button first, and it will lead us to a job creation page. We need to fill in some basic information for this job, like the job name and job description. Then we need to select a team owner for this job, and then the job schedule. We have some preset schedule here. Let's say it is a daily job, and we can see it will be kicked off at 12 a.m. in the morning every day. Then we'll go to the job start date. The job start date can either be a future date or previous date or current date. So if we select future date, means that the job will only start running in some date in the future. But if we select some past date, it means that this job is a backfill job, and it will do all the backfill starting from the job start date you're giving. And this one is the how long we are expecting this job to be finished. Let's say we're expecting this job to be finished within 1 hour. After 1 hour, if the job hasn't been finished and it is still running, it will send alert to the following email address you're giving. Let's give in the email address here. And the next thing we need to do is to specify a task. Task is a basic execution component within one job. And within one job, we can have multiple tasks. And then we can define the dependency relationship between different tasks. We have a list of different task types to choose from, basically from 3 categories. The first category is the creation. We support 3 different queries, High, Presto, and Spark SQL. We can also set dependency here. We can set dependency on dataset, S3 location, or have table. And we can also do table validation here. We can validate a table, and we can also publish the availability of one dataset. In this demo, I'll create 3 tasks, 1 from each category. Let's start a dependency. Let's say we will wait for one dataset to exist before executing the following task. So this task will be waiting for this table, and we will only check if the table exists, and this table is a non-partition table. We will uncheck this and click OK. For the second task, we will use the first category, creation. We want to create a new table based on the previous old table. We call it create new dataset task. And we can put a query here. Basically, it is creating a new table based on all the data from the old table. Because it is a demo dataset that doesn't contain PI data, so for the CCPA tagging part, we will select no PI. And then the next thing is dependency. Because this task can only be run after the first task is successful, so it will depend on the first task, which is the wait for data. Atlas also support query validation. If your query has syntax error, like this, when you submit a task, Atlas UI will stop you and show you where the error is. And then we will create a third task from the data quantity category. We will publish the dataset after the second task is done. Let's call it publish dataset. And we are publishing the availability for this particular table. And it will depend on the second task. I click OK. And this is all the information we need. Then we click submit. As you can see, the new job is created. Apart from the job details, if you want to check the running history of each job, we can go to the History tab. If you want to check the task level running history, we can expand here. On the top right side, we have the control panel, where we can edit and update a job. We can pause and unpause the job, and we can delete a job. This is a quick demo on the Atlas, and let's go back to the slides.
Thanks, John. With all things Zillow, we love our Z's. And with that, I'll talk a bit about Zagger. So Zagger is aimed at providing a developer-friendly abstraction on top of ETL tools. Primarily, it constructs the actual pipeline from a config definition and automates a lot of the ancillary tasks that data engineers do when creating a pipeline. We've chosen Terraform as our UI layer, as our users are familiar with infrastructure as code, and we can use things like autocomplete and entity relations that Terraform provides. We've created Terraform resources that cover common pipeline patterns that we see, allowing teams to quickly stand up a pipeline that follows a common structure. Terraform talks with Zagger's REST API, and we've developed this API first, allowing us to focus on building out integrations and onboarding as many new pipeline processing blocks as possible. Our target users are primarily data producer teams within Zillow that want to create their own data pipelines, but we're also designing it such that data engineers like myself can use this tool to enhance their development experience. Now, let's dive a little bit deeper into the actual structure of Zagger and the integrations that it provides. When we refer to Zagger, we're referring to two things. So first is the Zagger Pipeline Utilities, or ZPUP, that we see at the bottom of this slide. This is where all of the actual parsing, rendering, and data pipeline templates are implemented. We've decided to go with this library approach because we first and foremost want to develop tooling that everyone within Zillow can use without being dependent on our service. We see our service as one potential avenue through which a developer can use our package, but we don't want it to be the only avenue. Second, we have the Zagger Managed Service, or ZMS. So this is the service that we run, which when accessed through an API, will parse, render, and deploy the pipeline. Working left to right, we've designed this service with an access layer that's UI independent. Through standard REST access, a user can create the pipeline through Terraform, Zetless, or even GitLab CI/CD. We want to make this service as flexible as possible to allow for more UI tooling to be built on top of it. And looking into the ZMS section at the center of the slide, I'll cover a few key components of this design. So first, the service supports multiple interpreters and multiple renderers. Because these components are modular, users automatically get the flexibility of ZPUP just by using the managed service. Second, the managed service aims to automate or augment a lot of the ancillary tasks that data engineers do today. While we just have one integration shown, I'll provide a couple of examples to better explain. As a data engineer, I need to create a Hive table when I'm onboarding a new data source and want to persist that data into a table. The managed service is aware of the Hive table as referenced in the data pipeline, and given a schema, it will actually go out and create that Hive table if it doesn't already exist. If a user wants to integrate with Zillow's internal data quality platform, the managed service will check to make sure that the data contract ID referenced in the pipeline is valid. Moving to the bottom right of this diagram, we have the integration with execution. The managed service provides a way for users to leverage the internal processing libraries that our data engineers have created. As more processing steps are developed, we can continue to support those steps and more quickly give our users the tools that they need to create high-quality pipelines. Users can also configure which clusters their jobs run on, allowing teams to create and monitor their own production resources. Finally, we're looking to consolidate monitoring of production pipelines. Users of ZMS will be able to view the status of their jobs, monitor production failures, and view performance metrics of their pipelines in a single place. We do this by routing Spark job logs, Airflow or other orchestrator metrics, and internal monitoring services to a single place so that teams can visualize how their pipelines are performing in real time. And with that, I'll hand it off to Jan to talk about next steps and close us out.
Thanks, Derek. We started SelfService ETL platform development process back in 2019. The overall development process can be decoupled and divided into two parallel sub-processes. One for Pepper, which is a shared Spark processing library, and the other one is for the service, which renders the logic based on the processing library, like Zetless and Dagger. Zetless was started and launched in 2020, and it provides users with a UI-based tool to create pipelines. The development of Dagger managed service and the pipeline utilities package library was also started in 2020, and it provides users with additional access layers from Terraform and GitLab. In 2021, Zillow, which is the first version of self-service platform in Zillow, has been retired and replaced by Zetless. We are currently working on the unification of Dagger and Zetless backend. We also want to have a user growth in 2021. The first takeaway from our presentation is that the UI design needs to solve the pain point for the users when they want to create a pipeline without writing a code. We also learned that self-service ETL has bigger demands and a wider audience. Both engineers and non-engineers need self-service ETL platform to accelerate their workflow. The third one is that the modularization and the separation of the whole self-service ETL platform into different components has many benefits, like improved reusability of components, improved development efficiency, and easier to track issues. The last one is that the abstraction from the two specific implementation can provide better flexibility to satisfy user requirements. And the separation between the opinion layer and non-opinion layer provide us with the ability to expand if we want to introduce a new opinion layer in the future. More from Zillow on Thursday. Julian and Smith will talk about democratizing data quantity through a centralized platform at 3:15 p.m. PST. Cyan and Smith will talk about auto ML-driven anomaly detection with Luminar at 5 p.m. PST. In the end, please don't forget to read and review the session. Your feedback is important to us and help us to improve. Thank you so much for your time. Any questions?